This video lecture will explain the general principles for two-sided truth trees. By the end of the video, you should understand the following concepts. Which side of the truth tree is the true side, and which is the false side? When does a branch of the truth tree close, and when does it remain open? When is the truth tree as a whole closed, and when is it open? And what does it mean if the completed truth tree is closed or open? Things this video will not explain. It will not explain how we take apart the different kinds of statements in the truth tree. In other words, this video will not explain the rules for truth trees. I will be using these rules, but I won't explain them. In this video, I just want you to focus on the general concept of truth trees. For an explanation of the truth tree rules, see the other two videos on truth trees. The video entitled Right-Hand Truth Tree Rules, and then the video entitled Left-Hand Truth Tree Rules. Another important note. In this video, I will be using an argument from propositional logic to explain the basic concepts for truth trees. The important note is that the basic concepts remain the same when doing truth trees for predicate logic. Okay, with all of that in mind, let's get to work. We will start by putting our premises and conclusion into the truth tree. So our truth tree will have two sides, the true side and the false side. So the true side is the left-hand side of the tree, and the false side is on the right-hand side of the tree. So we put our premises on the left-hand side of the tree, the true side, and we put our conclusion on the right, the false side. So why are we doing this? Basically, the idea here is that we are starting out by assuming that the argument is invalid. We're assuming that it's possible for all the premises to be true. That's why the premises are on the true side of the tree. And for the conclusion to be false. So that's why the conclusion is on the false side of the tree. We will then take apart all of the formulas in the tree until we have reduced them to single letters. Never mind for the moment how we will do this. And see if this assumption, the assumption that it is possible for all the premises to be true and the conclusion false, leads to a contradiction. I'll explain this idea in a second. If so, then our assumption that the argument was invalid was incorrect, and the argument is in fact valid. So what does it mean for the truth tree to lead to a contradiction? To explain this, we need to discuss the concepts of closed and open branches on the same tree. A branch on the truth tree closes whenever the same exact formula can be found on both sides of the branch. For example, if we had the formula A on the left-hand side of the tree, and then also on the right-hand side of the tree, then the tree would close, because this is a contradiction. What this says here is that the formula A is both true and false, which is nonsense. It's contradictory. Thus, this branch has led to a contradiction, so we close off that branch, as I said. Note, it doesn't matter what the formula is. It can be any formula. So we could have not A and not A, and the branch would close off. Or we could have A arrow B on one side of the tree, and then A arrow B on the other side of the tree, and it would close off. Any formula at all, as long as it's the same exact formula on both sides of a branch of a tree, then it closes off. a branch on the truth tree is open if your tree does not have the same formula on both sides of the branch. So if we had A on one side of the tree, and then maybe we also had A on a branch further down, well, this wouldn't close off because they're on the same side, so there's no contradiction there. And the branch on the truth tree can only be considered open if all of the formulas in the tree have been fully decomposed. I will now illustrate this concept of open and closed branches some more by completing the truth tree that I started earlier in the video. Okay, so we will start with the first premise. So we'll take that apart. We get C and not S there. And then we get a T on the inside here. And you see that now we have a T on the left-hand side of the tree, and then also a T on the right-hand side tree, further up the branch. So this branch right here will close off. This one will not, at least not yet. The next thing I'm going to do is I'm going to take apart the second premise. So we'll get not C and S here. We'll get T here. And so again, this branch will close off because we have a T on the left-hand side of the tree and a T on the right-hand side of the tree. Okay. Then I'm going to take apart this premise up here, this formula up here. So it gives us not S here and C here. And nothing closes off on either of these branches, so we need to keep going. And then we take apart this one, and since we have two open branches, we need to do it on both branches. So we get a not C here, and an S here, and a not C here, and an S here. Okay, now we have to take care of these negations. So I will do the not C, so that becomes C on the other side. And so now this branch closes off because I have a C on the left-hand side of the tree and a C on a right-hand side of the tree. This S here, however, everything on, if we follow the branch up, everything is decomposed, and there's no S on the other side of the tree. So this branch here will remain open. And then we do the C here. Now, although we've taken apart this, we've done this C on this branch, here it remains open because as we follow the branch up, see there's a C, but it's on a different branch, so it doesn't close off. And then finally we do the not S, so that gives us an S on this side of the tree, and so this closes off because we have an S on both sides of the tree. So this truth tree is, we have now decomposed all of the compound formulas in the tree and closed off all the branches that we can. However, we are left with two branches that remain open. So what does this tell us about our argument? First, we need a bit more terminology. So a truth tree is closed if all of its branches are closed. A truth tree is open if at least one of its branches remains open once all of the formulas in the tree have been decomposed. So if we go back and look at the truth tree we just finished, we see that this truth tree is open because we have two open branches. When a truth tree is closed, that means that every possible way that the premises might all be true while the conclusion is false led to a contradiction, because that's what causes the branch to close. and thus your original assumption that the argument is invalid, that it is possible to have all the premises true and the conclusion false, was incorrect, and thus the argument is valid. However, if your truth tree is open, that means there is at least one way that the premises might all be true and the conclusion false. Since if your truth tree is open, there must be at least one branch that did not lead to a contradiction, and thus your original assumption, hypothesis if you will, that the argument is invalid, that it is possible to have all the premises true and the conclusion false, was in fact correct, and thus the argument is invalid. In fact, in a minute I will show you how you can read a set of truth values that proves this invalidity, read a counterexample right off the truth tree. So to sum up this discussion, if your truth tree is closed, then the argument is valid. If your truth tree is open, then the argument is invalid. Okay, so returning to the truth tree we just completed, as I said, we see that we have two branches that remain open. Thus, we know that this means that the argument is invalid. So now let me show you how to read a counterexample off the truth tree. So we pick any of the open branches. So I'm going to pick this first one here, the one that starts with the S. And you just read the truth values off the tree, off the truth tree. So we need a truth value for C, and for S, and for T. So looking at that open branch, we see that S is on the false side of the tree, so we'll make S false. Then moving up the tree, we see that C is also false, so we'll make that false. And then T is also false. We would get a different answer if we had used the other branch. So if we'd used the other open branch, we would see that C is true, because it's on the true side of the tree, and there actually is no S on this tree. But actually there would be if we had decomposed the not S right away instead of doing it on. So actually that should have been here, because we should have done that on every open branch. It didn't make any difference. But that tells us that, okay, S would be true. And then we have T still false. And we can check both of these counterexamples and see if they in fact make the premises all true and the conclusion false. So if C is false, well then the antecedent of this conditional is false, and so the conditional as a whole is true. Likewise, if S is false, then the antecedent of the second premise is false, and thus the conditional is true. And then we have T is false makes the conclusion false. If we have C true, but then we have S true, well then that makes not S false. And so again, the antecedent of the first conditional is false under the second set of truth values, and so the conditional is true. And we will also have the antecedent of the second conditional of the second premise will be false, because we have C is true, so that makes not C false, which makes the antecedent false and then the conditional true. And here again we have T is false, so the conclusion is false. So either of these is a counterexample is a set of truth values that shows how it's possible for all the premises to be true and the conclusion false. So we can extract that from our truth tree, and that serves as an important check to see if you've done your truth tree right. Note, if it checks out This does not necessarily mean your truth tree is 100% right, because you could have gotten the right truth values for the wrong reasons. So you should still double check all of your steps in the truth tree as well. So that's the basic idea behind double-sided truth trees. So to sum things up, the important things to keep in mind with truth trees are: write your premises on the true side, the left-hand side of the tree, and your conclusion on the false side, the right-hand side. As you decompose your formulas, you will need to keep this idea of the true side of the tree and the false side of the tree in mind to make sure you decompose the formulas correctly. More on this in the videos on the truth tree rules. A branch on the truth tree closes whenever the same exact formula can be found on both sides of the same branch. A branch on the truth tree is open if your tree does not have the same formula on both sides of the branch, and if all the formulas in the tree have been fully decomposed. A truth tree is closed if and only if all of its branches are closed. And a truth tree is open if and only if at least one of its branches remains open once all the formulas in the tree have been decomposed. If your truth tree is closed, then the argument is valid. If your truth tree is open, then the argument is invalid. We can read a counterexample off any open branch in the tree by working our way up the branch from the bottom or down from the top, noting the truth value of each formula as we go. If the formula is on the left-hand side of the tree, the true side, we mark it true in our counterexample, and if it is on the right-hand side of the tree, the false side, we mark it false. It's just that simple.